Just a little note, when I start working this problem, I very cleverly decide to leave out this capacitor because I don't really like capacitors, so I just left it out and ignored it. But then I decided I better put it back in, so later on in the problem you'll see I put it back in. So let's take a look at this circuit. So we have an input current source, which is 2 cosine 1000 t amps, and we have an input voltage source, which is 8 sine 1000 t volts. So those are not in phase. And it's to be connected to a load circuit that provides optimum performance when the impedance Z of the input circuit is purely real. The circuit includes a matching element whose type and magnitude should be chosen to realize that condition, and what should those attributes be? Okay, so any ideas as to how we want to go about doing this problem? First of all, do we want to leave it in terms of cosine and sine, or should we change it to phasors? What's that? Yeah, so it'd be better to do phasors. And so we know that for the resistance, it'll just be the resistance. For an inductor, we know that we would have J omega L would be the impedance of the inductor. If we had a capacitor, we don't yet, but we might add one. If we add a capacitor, it would be minus J over omega C. And what would our current source be as a phasor? Well, if I had it as a, okay, so I know what you're thinking of, and it's what you're thinking of is if I had 4 plus 3j, then theta would be the inverse tangent of 3 over 4. But if I have it as a function, if I have something like the voltage as a function of time equals 32 cosine 60 t plus 45 degrees, then this is my angle right there, just the angle that's given. And so in our example, we have just I of t is 2 cosine 1000 t plus 0. So our angle is just 0. And then how do we switch from sine to cosine? You're close. Yeah, so it's just 90 degrees. Yeah. Minus or plus 180 would be to make the get rid of the negative for a cosine. Whoops. It's 8 sine 1000 t, which makes it 8 cosine 1000 t minus 90 degrees. Let's see, is that right? So if I have sine And then if I take cosine and I shift it right by 90, that gets me sine. Yeah, that's right. Okay. So our voltage would be 8 angle negative 90 degrees. Which is the same as if we have that angle and we think about our complex plane, where this is the real and this is the imaginary. Where am I if I go to negative 90 degrees? Yeah, and that's just on the imaginary axis. So this is the same as minus 8j. So, and I can check that. So if I had 8 angle negative 90, it's the same as minus 8j. And then also, just to show so if I go to I'm in radians here, but if I put in sine x and then I put in cosine x minus, and then in radians 90 degrees is pi over 2. You see that those really are the same. So subtracting 90 degrees from cosine gives us the same as the sine. Okay, so we have those. So now we can redraw this as our current source is negative 8j amps. Oh, and by the way, omega, what is omega? It is 2 pi f. What is it in this problem? So omega is 1,000. So this will be 6 because the resistor doesn't change. This will be J times 1,000 times 4 millihenries. So 4 millihenries is 0.004. And these will now all be in ohms. So this is 2 ohms, and our voltage source, oh wait, no, I was 2, angle 0. And V was 8, angle -90. And then we have our matching element that we're going to put in here, and then we'll have our load over here. So we can replace this with 1 impedance. 1,000 times 0.004 is just 4. So this would be 6 plus J4 ohms. Okay, so any ideas what we would do here if we're trying to get the equivalent impedance of the rest of this circuit?
I guess that's parallel with that. Something like that.
So what's parallel to what?
6 plus J4 is parallel to the resistor.
So it's not quite parallel because the resistor, the other end, to be parallel, they have to have their ends at the same voltage. And these don't have their ends at the same voltage because this one, if this was ground, this would have this end at 0 and this one would be at 8 angle -90. So their tops are at the same voltage, but their bottoms are not. And so what we can do to get them to where they are parallel is to do a source transformation. Okay, so whenever you have a voltage source and a resistor in series, you can change that to a when you have a voltage source, so voltage source plus resistor in series is equivalent to a current source and resistor in parallel. And we could either change the voltage source and the resistor to a current source and a resistor in parallel, and then we would have things in parallel, or we could change the current source and the impedance that are, I say resistor slash impedance. or I could change the current source and the impedance that are in parallel to a voltage source and a resistor in series. And in this instance, it would be easier, I think. So let me show you what our two alternatives would look like, and then we'll see which way we want to go. So if I transform the right two, then what I would end up with would be I would have something that looked like that. And I don't really like that, because then I still would have like this point here where I would have to do some voltage division or something. But so this would be transforming these two to a voltage source and an impedance. So if instead we transform these two, what we'll get is something that looks like this. So we'd have our original current source and our impedance. So this was 2 angle 0 and 6 plus J4. And when you do this source transformation, your current source is going to equal your voltage source over your impedance. So this would be your transformation. So your new current source equals your original voltage over the impedance. If we did it the other way around, then our new voltage source would equal our original current source times the impedance. But the impedance doesn't change. So that's going to be 2 ohms. And so this is going to be 2. No, it was, what was the voltage? It was 8 angle minus 90.
Yes.
And then divided by 2. And when you have things in parallel, there's nothing special about the order that they're in. You can rearrange them to be in any order. So 8 angle negative 90 divided by 2 is now 4 angle negative 90. Six plus J4. And 2 ohms. And now current sources in parallel just add. So this is 4 angle negative 90 is the same as minus J4. And 2 angle 0 is the same as 2. So this is 2 minus J4. And then to get our equivalent impedance, we'll do product over sum. And then I see that everything here is divisible by 4. Normally I'm lazy and just use a calculator, but this one is easy enough for me to do. So I will multiply by the conjugate, and I get 6 minus 3j plus 4j is plus j, minus 2j squared is plus 2 over 4 plus 1. Equals 8 plus j over 5, which equals 1.6 plus j.2. Oops. Let's see if I did that right. No, I didn't. Did I lose an entire... Oh, that's a different problem. Did ours have a capacitor in it? Oh, it did have a capacitor. That makes it a completely different problem. Okay, let's throw that capacitor in there. So the capacitor is 0.5 millifarads. So 0.5 millifarads. So minus j over omega c. So that's minus j over 1,000 times 0.5 milli is 0.0005. So that's minus j over 0.5, which I believe is minus 2j. It's minus 2j. So then that changes everything. So I still have this minus 2j in there. And a minus 2j in there. Wow, that's bad. Minus 2j. So I found the equivalent impedance of the first two I was very pleased with myself, but now I have this is in parallel, so I have 1.6 plus 0.2j. That's in parallel with a minus 2j. So to get those, I would have 1.6 plus 0.2j times minus 2j over 1.6 plus 0.2j minus 0.2 minus 2j. So that's minus 3.2j plus 0.4 over 1.6 minus 1.8j, and now I break down here. So I'll bring it back in just a second. So we had minus 3.2j plus 0.4 over 1.6 minus 1.8j. And that's right. Yeah. Okay, so that gets us 1.1 minus 0.76j. So now our equivalent circuit has, we had a current source, right? A current source and an equivalent impedance. And we have our mystery over here. And our current source was 2 minus J4. And this is 1.1 minus 0.76j. Okay, well, now we want to get it to where these are in series with our component that we're trying to add. So we'll do a source transformation back to a voltage source. So I don't really care what the value of the voltage source is. It's 2 minus J4 times 1.1 minus 0.76j, whatever that is. And then I have an impedance of 1.1 minus 0.76j. And now I want to figure out what kind of component can I put in here so that my total impedance is entirely real. So what should I put in there to have an entirely real impedance? So it should have an impedance that when I take 1.1 minus 0.76j plus this z, I get a real number. So of course it could have any real part at all that I wanted to. So we need to get a real number here. And so we need whatever we add to 1.1 minus 0.76j to be a real number. The imaginary part that we have is negative. So we need to add a positive part, and of our components, inductors are positive imaginary j omega L, capacitors are negative minus j over omega C. And so if we are trying to get rid of the minus 0.76 J part of the impedance, we want j omega L to equal minus 0.76 J. The J's cancel. Omega is 1,000. 1,000 L equals 0.76. Divide by 1,000, and we get 0.76 millihenries is the component that we needed to add. Okay, so any questions on that? All right.